Hello students, today we will study sounds chapter and in the lecture 2 we will study regarding the speed of sound and reflection of sound. Okay, a little bit you have studied in class 8 but in elaborate just I will give you the concepts very clear. So let's start with the speed of sound formula. Now here speed of sound. Now we know that speed of sound that depends upon the medium. That means, and also we have studied that is for solid, for liquid, for gas. There may be three types of medium, and for these three types of medium, the sound speed is different, right? And for solid, we have studied the sound speed is fastest, and here it is our moderate, and for gaseous material it is our slow, right? And we have also studied a chart where it has been mentioned whatever the sound for through the sound speed through the water and air and also copper metal. Now the speed of the sound, if it is denoted by V, so that equals to lambda into F. So this is the speed of the sound, where lambda is the wavelength, and already I have told you if this is the waveform, then lambda means this much. Lambda means this much. And F, that equals to 1 by T. That means it is inverse to the time taken to travel a distance. So that is the V equals to lambda by F. So please remember this thing. So this is the velocity or speed of the sound through any medium or any medium. But again, I am saying you, please understand one thing, that sound cannot travel in the through any vacuum, and it has been experimented by us in the previous lecture. So the wavelength of the sound, that is the distance between the adjacent completion and rarefaction. This you know already, but I have just given here just for brush up purpose. And the frequency is the same as the sources and is the number of waves that pass a point per unit time. Next, how long does it take for a sound wave of frequency 2 kHz and a wavelength of 35 centimeter to travel the distance of 1.5 kilometer, right? So this is an example, and we'll do this type of so many numericals also. This is an example only. So here, as you just now you have studied, just a minute, I'm just changing the pointer color. Just now you have studied what? That V equals to lambda into F. Okay. So V equals to lambda into F. So if we substitute the values, lambda is how much? That is our 0.35 meter, and into 2000, 2 kilohertz, that means 2000 hertz. So that will be our 700 meter per second. Now the time taken by the sound wave for to travel the distance, how much? That is 1.5 kilometer. So the time, that is the distance traveled by velocity. So velocity, already you know that the velocity is 700 meter per second. So time is how much? What will be the 1.5 kilometer? This 1.5 kilometer, this is nothing but 1.5 into 1000 meter, that is nothing but 1500 meter. So your time taken, if it is denoted by T, that is 1500 divided by 700, that is 2.1 second. Okay, is it clear? So now whenever there is a wavelength of 35 centimeter, at that time what will be our velocity that we found, and to travel 1.5 kilometer, what will be the time required? That also we found. Fine. So in this way, the numerical you can solve, and I will give you so many numerical also we'll solve in the lectures also. So that we'll do. Now, the factors affecting the speed of the sound. This is very true that for the to travel the sound, we require some medium. But there is some properties of the medium that affects the speed of the sound. That affects the speed of the sound. That affects that speed of the sound. Okay. So here, let me change the color. Okay. Now, first is the density of the medium. First is the density of the medium. Now, whenever the density that is high, that means what? The molecules in the medium are closely packed. Like for the solid, the density is highest. So, at that time, the molecules in this medium are closely packed. So, the speed of the sound increases as the density of the medium increases. Okay. So, you should remember this thing, that density of the medium, it depends on the density of the medium. Now, when medium is dense, at that time, the molecules in the medium that are closely packed, so that the sound travels faster. That means speed of the sound increases as the density of the medium increases. Okay. So that means if density of medium increases, speed of sound increases. Fine. Next is the temperature. Now, speed of sound is directly proportional to the temperature. That means if temperature increases, speed of sound increases. Okay. So this is the relationship. Please remember this thing. So in this slide, what we have studied, first thing, as you have told that the sound that will travel through a medium, that means some characteristics of the medium, characteristics or some parameters of the medium that will detect how much its speed will be there. So first is the density of the medium, and second is the temperature of the medium. So density, if more dense, then more faster will be sound travel. So if temperature increases, then at that time also the sound speed will increase. Clear? I think there is no confusion till now. Next, move to the next one. That is the speed of the sound that depends on the density and elasticity of the medium through which it travels. And sound travels faster in liquids than gases, quicker in solids than liquids. And greater the elasticity and the lower the density, faster sound travels in medium. So we know that for the solid, here fastest sound travels fastest, then liquid. Here elasticity is moderate. So moderate. Again for gas, that is low. Fine. So this thing, speed of the sound, that depends on the density, also temperature, and that we have studied till now. Now speed of sound in solid. Now in the solid, the sound, what is sound actually? Sound is nothing but the vibrations, and how the vibrations may happen if this is a solid and you have one molecule here, another molecule here, there will be collision. And due to these collisions of the between the particles, one molecule hitting the next one and so forth. That means you just imagine this case. In your school classroom, all of you are just sitting in a bench. Suppose three students, they are sitting in a bench. So if one will vibrate or one will just vibrate, then another person will vibrate, next one will vibrate. Similar thing. If this will collide with this point, then you can see that there will be vibration. Again, it will be energized and it will collide with another one. Okay, nearby one. So that means here the solids in this case, here you know that so many molecules are there, and in this case if it will vibrate, then you can see that it will just try to change the move, it will try to move another particle, but it will not move because there is no space, only it will vibrate. Then this vibration will be transmitted to another particle, then another particle, next particle. That means whatever the neighborhood particles, all those particles will be in vibration. So due to this vibration, there is a creation of the sound. So that's why in solid you can see that the sound, that speed of the sound is highest. Okay. So the closeness due to the density means that they can collide very quickly. In case of sound, as I have told you, that if in a particular area, in a particular medium, a lot of you have a lot of particles. You have in a particular area, you have lot of particles, lot of particles. So if it will move, then it will vibrate, and another one will vibrate. And here also you can see that the next one will vibrate. So that means what? So what I have said, that so many particles are here, and if you have so many particles here, that means if one particle will vibrate, at that time you can see that this vibration, it cannot move otherwise, because there are so many neighbor particles are there. So what happens here? At that time you can see that the neighborhood particle, this will vibrate. So due to this vibration, the sound will be generated. That means the sound has been produced due to the collisions in between the particles. Collisions in between the particles. Okay. So this happens in case of the solid. Let's see the next one. That here you can see that the speed of the sound in solid, that is 6000 meter per second, while the speed of sound in steel is equal to 5100 meter per second. Can you imagine how much is the speed of the sound? It is so high that you cannot per second it will travel 6000 meters. So that means a huge velocity is there, huge speed is there. So another interesting fact is that speed of the sound, that the sound travels 35 times faster in diamonds than in the air. Diamond is the hardest particle you have, hardest thing you have. So here, hardest object. So in case of diamond, the sound travels 35 times than the air, 35 times. So a huge velocity or speed will be there, right? Next, speed of sound in liquid. Now, in case of liquid, okay, this is a surface where we have the liquid, and in case of liquid, you can see that the particles, these are not so much near. Here, what happens if it will collide? There is a space, or interatomic space is a little bit large rather than the solid. Here, the distance between the molecules are more in liquid than the solid, but less than the gases. So hence, speed of sound in liquids lies in between speed of sound in a solid and gas. Collision will be there, but the distance is high. So vibration at this time, that is a less amount of vibration. So you can see that at that time, the sound speed, that is also little bit less than the solid one. Next, the speed of sound in water. Speed of sound in water is 1480 meters per second. 1480 meters per second. And it is very interesting that speed may vary from 1450 to 1498 meters per second in distilled water. So here you can see that we have the speed of the sound in water that is high than the air. In case of air, what we have studied, it was only 330 meter per second. But here you have the speed that is 1480 meter per second. Okay, and in it is also interesting that the speed also changes. That means what type of water you have, distilled water or only simple water. So that also depends. And sea water, in case of sea water, that speed is 1531 meters per second when the temperature is between your 20 degrees centigrade to 25 degrees centigrade. That means what we have studied in this lecture, in this slide, we have studied that in case of our water, here we have 1450 meter per second, and in case of our distilled water, that is our 1498 meter per second, and in case of sea water, we have the speed is 1531 meter per second. Okay, 1531 meter per second. Fine. So speed, these are the speed of the sound in liquid. Now speed of sound in gas. So that we'll study. So we will study that is the speed of sound in gas. Now here in the gaseous medium, what happened? Suppose this is the gaseous medium and here the molecules, they are the distance, intermolecular distance between these two. Intermolecular distance between these two is very high. Intermolecular distance between these two is very high. So at that time, if one molecule will vibrate, it does not that mean that other molecule will vibrate. So speed of sound here is very less because the vibration is very less amount. So the speed of sound in gases is proportional to the square root of the absolute temperature. Square root of the absolute temperature. Okay. Next, here you know that the speed of sound in air at 20 degrees centigrade, that is how much? 343.2 meter per second. This is for 20 degrees centigrade. And you know that, just a minute. You know that this may differ whenever the temperature will be different, right? So here this is the speed of the sound through the gaseous medium. Now, speed of sound in vacuum. Previously, I have told that in vacuum, there will be no sound you can hear. And in the case of bell jar experiment, already we have seen that yes, it is not possible to hear any sound whenever this bell jar is vacuum. Okay. Now the speed of the sound in vacuum, that means it is zero. It is zero meter per second. It is 0 meter per second. And the sound waves travel in a medium when there are particles. For the propagation of these sound waves, at that time, I think that yes, the sound waves will travel, right? There should be some particles. But in case of vacuum, this is an empty space. There is no propagation of sound waves. So in vacuum, it is not possible that there will be any propagation of sound waves. Fine. Okay. So here in a tabular form, I have given a lots of the speed for every material that we are using, but you just keep in your mind the data are not so much important of the density, but this data is very important in accordance with the speed. Like copper, it is 6480. For your water 1496, and air, that is 331.45. Now you can ask me one question, ma'am. It has been written 331.45, but previously you have said that 342 around something. So actually, whenever the temperature changes at that time,
that time that speed also changes. So it has been taken in different temperature. But in the previous case, what was 342, 342 meter per second, approximately this one. This is for 20 degrees centigrade. Okay. Now, shearing. Now you know that sound waves can be created either by compression or by tearing of the solid. And this is known as shearing. Okay. So let me take the highlighter. So sound waves can be created either by compression, or by tearing of the solids. That is known as the shearing. Now, these waves exhibit different properties from each other and also travel at different speeds. So now you have seen earthquakes. Now earthquakes, those are created due to the movement of earth plates. What happens? There is a plate here and there is another plate here. But if one plate that it has some movement, at that time, this vibration or this disturbance that will create some waves similar to the sound waves through the earth and to the surface, that causing the earthquake. Okay, due to the plate displacement, it will create some earthquake. Sometimes you know that like tsunami also, it is due to the some displacement in the plates whatever under the sea. So that thing also may happen. So earthquakes that happens, and due to the earthquake, if we are seeing in the seismograph, at that time we can see some wave nature of the earthquake and it looks like the sound wave. So here that I have told you regarding the seismograph, in the seismic terms, the compression waves that are called P waves and the tearing waves that are called S waves. Okay, so compression waves travel faster than the tearing waves. Compression wave that travels faster than the tearing waves. So earthquakes always start with an up and down motion followed after some time by the side to side motion, right? After some time, there will be some side to side motion. Okay. So here, so if they are more destructive, this shearing, and these are more destructive and they can make some great damage. Now the reflection of sound. Now reflection of light, you have heard this term. Now here we will study the reflection of sound. Like light energy, the sound also, it reflects. But here we require one reflector, that is hard surface. Now here I can show you, this is that speaker, or I can say source of sound. Okay, and this is the incident sound wave. Fine. And this one, this is the reflector, and whenever it is coming back to the same medium, this is the reflected wave. Okay, so the sound that is coming from any source, that may be speaker. So whatever the, this is incident sound wave, then it will strike in the reflector, again it will come back, but it will follow the different path, it will come back, and it is called the reflected wave. Fine. And two laws, those are followed in this case. Two laws, those are followed in this case. Suppose you have this reflector, you have, this is the reflector, and some incident wave is there. Sorry, just a minute. And some incident wave will be there. Whenever it will strike at the reflector and it will just follow another path, it will be reflected back. If I draw a line that is normal, that means this will be your 90 degree. That is normal. So it is called normal. Okay. If I draw here, then I can draw the normal like this. So here this is called normal. Now, first thing, this is our incident angle theta I, and this theta R, this is our reflected angle. So first law is that angle of incidence is equal to the angle of reflection. So that means theta I, that should be equal to theta R. Then incident sound, normal sound, and this should be reflected sound all lie in the same plane. The incident sound, reflected sound, and the normal sound, all these three will lie in a same plane, in the same plane. So these two rules, these two laws, these are applicable for light as well as for our sound also. Fine. Let's move to the next slide. Now, this sound reflection we are using in several daily applications, right? Like we are using in case of stethoscope, we are using for our megaphone, we are using for our like whenever we are using some megaphones, whenever we are using sound system in a concert hall, okay, arc shaped wall we are using, okay. So this reflection we are using in several applications. Let's see the first one, that is the stethoscope. What you have in stethoscope, one knob is there like your earphone, and here there are two pipes like this, made up of plastic or rubber. It may be rubber, not made up of plastic. And there is some circular disc here. And this circular disc, actually what the doctors they are doing, they are keeping it on the chest, right? And these two will go to the ear, look like earphone. So this wall, this is the surface 1, and this one is the surface 2. This is a hollow tube, surface 2, and this portion is the hollow tube. So this one is our surface 1, and this one is our surface 2, and this is our hollow tube. Fine. So first, the sound from the chest, that means what are the sounds? We have the sound of heartbeat, of lungs. So this sound is then incident on it. Whenever it is incident on this wall, then it will reflected, again it will be reflected, again it will be reflected, again it will be reflected. Like that, it will move and it will come to our ear. So here you can see that this is the incident wave. Then it will reflect from this surface point. Then again, it is the incident wave for surface 2. Then it will reflect, then again incident. So there are multiple reflections here, and after multiple reflections, you can see that the sound energy or the sound wave that reaches to our ear, and we can hear the sound of our heart and lungs. Now, if you have any cough in your lung, at that time also the sounds are different from the normal lungs. So at that time, the doctors may diagnose, yes, you have some problem in the lungs. Okay. According to that, they can give you the medicines, or according to that, they can suggest you some other X-ray, chest X-ray, or some other diagnostic equipments also you have to use, right? Next, the soundboards and curved ceiling or walls of a large halls. In the concert hall or in a large hall, we have the carved ceiling. Why? Here you can see that this is the carved ceiling or sounding board. Now this is the source, and this is suppose speaker. So from this speaker, the sound will move in this way. So this is the incident and it will reflect back. And after reflection of all the waves, you can see that the waves are moving parallelly. So the parallel sound waves, they can reach in a very this they can reach up to this much. It is not like that it will reach up to this much. That means if audience one audience is sitting here, he or she can hear the sound. Also one audience, he or she can hear the sound who are sitting here. That means throughout the hall, who are the audiences, they can hear all the sounds very clearly. That's why the sound reflection we are using in case of our any concert hall or any other hall where we are making some functions. Okay. Next, the megaphone. Megaphone, this is a horn shape. This is horn shape tube. Horn shaped tube. And in megaphones, you can see that this in this hollow tube, multiple reflections are happening. And after that, whenever in a wave, the sound energy or the sound wave, it is just coming out and they are parallel. They are parallel. So you can see the megaphone use of the megaphones whenever some announcement will be there. At that time, it can be used. So these sound waves, they are parallel and they can travel a long distance. So from a long distance person, they can hear this type of sounds. Okay, they can hear this type of sounds. Another thing that is the ear trumpet or hearing aid. Now, in case of aged person, you can see that they are requesting us, please talk to me loudly, otherwise I cannot hear. So that means there is some problem in their ear due to the aging also. It may be there is some problem so that they cannot hear the low voice sound. So or low voices or low sound. So what you have to do at that time, you have to shout to make them clear whatever your sentences. So that means they have to use some equipment, that is the hearing aid they have to use. That in that case also the sound waves received by the wide end of the trumpet are reflected into much narrower area, and that causes the increase of amplitude of the vibrating air inside their ear and helps in improving the hearing. Okay, and it will help to improve the hearing process. Fine. So when sound hits a hard surface, what we have studied, when sound hits a hard surface, at that time, just a minute, at that time it reflects back to its source. This reflection of sound is otherwise called an echo. Now, this echo I will elaborately tell you whatever echo and how it can be done, all these things. But one thing you listen, just you have seen also, whenever you are going to hill station and you are uttering your name, you can or you are uttering any word also, like physics. So you are echo, like echo. Suppose you are uttering echo. So echo, echo, echo. Several times it like that. There are some persons and they are uttering the same thing. So there is some echo also, and it is due to the reflection of the sound. And hard surfaces have the tendency to reflect the sound. So if you want to absorb the sound, then you have to use soft surfaces that will absorb the sound and silence them. Okay. So at that time we are using some soft surfaces. Thank you.